So today we're going to look at the graphs of inverse functions. And if you're familiar with inverse functions, there's one resounding thing that happens with them. And that thing is this. It's that the inputs and the outputs switch. So to look at that on a graph, what that means is I'm going to flop my x value, which is typically our inputs on a graph, and my y values, which is typically my inputs on a graph. So to demonstrate that in orange, I'll put a few points here. If I have the point 3, 4 on this graph, let's say it's right here. And if I have the point 1, -1, let's say that point is right here. And then if I have the point 0, 5, that point is going to be right here. These 3 points, we're going to look at what happens when I take the inverse of a function that may have these 3 points. And so in blue, we'll have the outputs. So if I flip the inputs and the outputs, if I flip x and y, that means that I am going to have the point 4, 3. And then I'm going to have the point -1, 1. And then lastly, the point 5, 0. Again, because I'm changing the inputs to the outputs of my inverse function and the outputs to my inputs in my inverse function. And so those points are going to look like this. The point 4, 3 is going to be right here. The point -1, 1 is going to be right here. And the point 5, 0 is going to be right here. And what do I notice? There's kind of a nice little symmetry to how these points are inverted. And one thing to realize here is that if my inputs and my outputs are changing, what's going to happen is there's going to be a reflection across the function y equals x. So if I draw that line real quick, I draw what y equals x looks like. It looks something like this. And I can then start to realize, this reflection is actually what happens with my points. This point reflected to here, this point reflected to here, and this point reflected to here. This actually gives me a really powerful way to describe inverse functions just by looking at the graph. So let's look at some of the implications of that on GeoGebra. Alright guys, here we're looking at Carroll College Math Department's GeoGebra page. There's a lot of good stuff on here. Today we're specifically going to be focusing on the function inverse checker, which is found right here. And if we go ahead and click on it, then we can see, making this full screen, that we have a inverse checker. If I have a function here, it gives me my line y equals x to reflect my function across. So for example, if I just have x plus 1, my reflection, the inverse, is going to look like that. And so our major question here today is, how do we know when the inverse of a function is in fact a defined function? And by looking at x to the second power, we can kind of see that. So if I look at x to the second power and its function, and then its inverse function in red, we can see that the red function doesn't quite look like it's a function. If you remember, we have this rule called the vertical line test. If I can make any vertical line that going through it, it crosses 2 different points, that means that this is not a defined function. So the red function in this case, the inverse of x squared, isn't a function because we see that it crosses 2 of the vertical line points. And so now we can start to ask, can we guess, just by looking at the regular function, if my inverse function is going to fail the vertical line test? And the answer is yes. Because if I realize what the reflection of a vertical line is across the line y equals x, the reflection of a vertical line is going to simply be a horizontal line. So take a look at this. if I make up a horizontal line, I realize that any function that fails this horizontal line test, in the same way I have 2 points that crossed a perfectly horizontal line, then that means when it's reflected across the y equals x line, it's going to fail the vertical line test. Let's take a look at x to the third power. So is there anywhere where my horizontal line is going to fail the horizontal line test on this blue function? If I drag it, maybe down here, but if you zoom in really close, you'll actually see that this is not a perfectly horizontal line on the blue function. So if I zoom in close enough, I will see it actually doesn't fail the horizontal line test. So that means that when I reflect this function, it's also not going to fail the vertical line test. In fact, I can drag it to the same exact spot. There's nowhere where this function fails the vertical line test. Now, if I add something else to the equation, like plus 2x squared, we might be in a different boat here. Because as I can see, my original function will fail a horizontal line test. So that means if I reflect it, I can expect my vertical line test to be failed by the inverse function. We can see here there are 1, 2, 3 points failed on the vertical line test. In the same way, around the same point, 1, 2, 3 points, and if the blue line fails the horizontal line test. So my grand conclusion is this. If my original function fails the horizontal line test, then that means my inverse function is going to fail the vertical line test, making it not a function. Alright, so here we have x squared in blue and x squared's inverse in red. And as we can see, we can predict whether or not red is a function. And for the red function, usually we would pull out the vertical line test and we would say, oh look, 2 points of intersection, so it's not a function. But now we can start to tell if the inverse is going to be a function by using what we call the horizontal line test. So since a horizontal line is going to go through 2 points of my original function, that horizontal line is going to reflect into a vertical line. And so if my function fails the horizontal line test, then we can say that the inverse of the function is not going to be a function. Let's write that out. So that means we can just make this conclusion that if f of x fails the horizontal line test, then f inverse of x is not a function. So now you can use this horizontal line test just by looking at your original function, and it will tell you whether or not the inverse is a function.